Okay, so we know how to use how to assign oxidation numbers. That's using this set of rules here. Remember? Okay, in the box. And now we're going to look how we can use oxidation numbers. Okay, so what we're going to say is, well, if you look at an equation, if no oxidation numbers change, then it's not a redox reaction. Okay, so you can identify if something is a redox reaction by assigning the oxidation number, look at the oxidation numbers, see if they change, and then see if it is. Also, in a reaction, if an element's oxidation number goes down, okay, arrow means reduce, it means that element is reduced in the reaction. And the converse of that, if an element's oxidation number goes up, then that means it's been oxidized. Okay, so let's use a few examples to let's do this. Now let's look at this equation here. This chlorine. Now, this you really wouldn't need to know oxidation numbers to tell that this is a redox reaction, because let's break that down. Whenever we get potassium and sodium, what do? We know that they're always a K plus sign, Na plus sign, so it's much better to write as an ionic equation. You can see what's happening. So let's rewrite that. So we're going to have Cl2, and this is halogen displacement reactions. You'd add chlorine gas to potassium bromide in aqueous solution, and you would make potassium chloride in aqueous solution, and you get some bromine produced, which actually does dissolve in water, so make the water go reddy brown. Okay, so chlorine, potassium bromide, break it down into its ions. It's 2 K plus ions and 2 Br minus ions. And that potassium chloride is going to be 2 K plus ions and 2 chloride ions. And bromine is Br2. Okay, bromine is covalent, so you wouldn't break that down into its ions. So we can see there that potassium is not doing anything, and that is always the case. Potassium never does anything. Okay, potassium ions just stay as potassium ions. Likewise, sodium ions just stay as sodium ions. They don't really get involved in reactions. They just float around. They've got noble gas electronic configuration. They stay as Na plus and K plus ions. But what we can see there is we can see that chlorine has gained electrons there, haven't we? So we know that reduction is gained, chlorine's been reduced. We can see the bromide ion has lost electrons, so it's been oxidized. And we wouldn't really need oxidation numbers to do this, but let's use oxidation numbers. So oxidation numbers then, doing okay, oxidation numbers doing green. Chlorine is an uncombined element, so Cl2, so it's 0 there. Whereas the oxidation number of chlorine in the chloride ion, well, it's got 1 electron it shouldn't have, so it's -1. So we can see that the chlorine has gone down, the oxidation number is going down, so it's been reduced. Bromine, well, uncombined element there, 0. And here oxidation number was going to be -1 because it's got 1 electron it shouldn't have. So we can see there quite clearly that the chlorine is reduced and the bromine is oxidized. Okay, and you might want to say, right, what's done the oxidizing there? It's the chlorine gas, so that's the oxidizing agent. And you might want to say the bromide ion is the reducing agent, because that reduces the chlorine, doesn't it? And it always causes a bit of confusing. We can see what's happened to the oxidizing agent. Well, the oxidizing agent gets reduced and the reducing agent gets oxidized. Okay, that's good. Right, let's get rid of that one and we will do another example. Right, so I've got another example down here somewhere. Right, this neutralization reaction here, sodium hydroxide and hydrochloric acid. Okay, let's move that up there and start doing that. Okay, right. again, it's a good idea to break this down into ions. So sodium is always Na plus, isn't it? So that means OH is OH minus. HCl is a strong acid, so it breaks into its ions, yeah, so it's going to be, acids always make H plus ions, don't they? Yeah, and chloride is going to be Cl minus. And then sodium chloride is an ionic solid, so that's Na plus and Cl minus. Now, I see loads of people here will start breaking the H2O down into ions. Well, of course, it's a covalent compound, so don't do that. So it's just H2O, yeah, right. Spectator ions, as usual, sodium doing nothing, and also the chloride ions doing nothing here as well, so we'll get rid of that. Okay, so oxidation numbers of oxygen in all of its compounds, except for hydrogen peroxide, always -2, so that's -2. So oxygen hasn't changed. Oxidation number of hydrogen is always +1 in its compounds, and +1 there. So no change in oxidation numbers. It is not a redox reaction. It's actually an acid-base reaction, isn't it? So, but anyway, so not a redox reaction, no redox there. Let's get rid of that one and do another one. This one down here. So let's get this one. Right, now again, this is one where we probably know already it is a redox reaction. Let's put it up there. We know it's a redox reaction because we know, right, sodium chloride is really, you know, it's Na plus and Cl minus, isn't it? Well, let's just make it balanced. Go on, do the whole, right? So we've got 2Na plus Cl2. I haven't got any spectator ions or anything there. Everything changes. Right, let's look at the sodium. Oxidation number of sodium there is 0. In Na plus, it's lost an electron. It's missing an electron, yeah? Electrons missing, yeah, we've got that over there. So that's got to be +1. And likewise, the chlorine uncombined element 0, but it's not missing any electrons. It's got an electron it shouldn't have, so that is going to be -1. Right, so we can see there from our oxidation numbers that sodium, it's gone up. Oxidation number has gone up, so it's oxidized. But again, we wouldn't really need oxidation numbers to work that out because, you know, sodium has become a sodium ion. It's lost an electron. Oxidation is lost oil. And likewise here, we wouldn't really need we can see here that the oxidation number's gone down. So it's been reduced, but we can tell it's been reduced anyway because it is gained. Reduction is gain. It's gained an electron from the chlorine. Well, let's just do what we did with the other one. Let's say what's sodium acting as here? Well, sodium's giving away electrons, so it is an oxidizing agent. And again, the oxidizing agent always ends up getting what? Getting sorry, the sodium isn't the oxidizing agent. Rubbish. It's the reducing agent. And the reducing agent always ends up getting oxidized. And look, the sodium gets oxidized. Yeah. The chlorine is acting as the oxidizing agent. Yeah, that's the right way around, isn't it? Because that is taking electrons away from things. And look, the oxidizing agent does get reduced. Right, let's do another one then. Okay, get rid of that. And these will become harder. So if you're getting a bit bored, I apologize, but let's have a look at a slightly harder one. Right, this one here. Okay, this one is slightly harder. So let's look at this one. Oops. Move that up there. Right. Now this one is maybe not quite so obvious what's going on there because you're thinking, oh, right, yeah, manganese. Well, anyway, so we will use oxidation numbers here, right? Now, I won't break that down. Well, actually, go on, I will break that down. We see, really see with this, it's a solid, and that's an aqueous solution. Okay, that's an aqueous solution. That's a gas, and that is a liquid. I'm not going to break down the MnO2 because it's not really an ionic compound. To be perfectly honest, it's a covalent compound. So I'm not going to do that. HCl, yeah, that's going to be 4H plus and 4Cl minus. The MnCl2 is a metal chloride in aqueous solution that is ionic. So that's going to be, well, you can probably work out the manganese ion must be 2 plus there, and the 2 chloride ions. And then you've got chlorine gas and water, which is covalent, so we don't break that down. If you did break this down into to ions, you'd actually be wrong. You might think that's the Mn4 plus ion and 2 oxide ions. You'd be wrong, but it would actually work out. It wouldn't make any difference to the way things worked out. But, you should know that M4 plus ions don't really form because it's losing too many electrons. Right, so MnO2, right, oxidation number of manganese there. Well, let's do oxygen. Oxidation number of oxygen. Oxygen is compound there, so it's -2. Oxidation is compound here, -2. So no change in the oxidation number of oxygen. Hydrogen, let's do that one. Always +1 in its compounds, and you can tell it's +1 because it's H plus there. +1 in water, so no change to the hydrogen. Right, let's look at manganese. Oxidation number of manganese there. Some charge in the species 0, each oxygen is -2, so that's going to be +4. There, +4 oxidation number. Whereas here, clearly, it's a 2 plus ion, it's lost 2 electrons, so it's +2. So yeah, the manganese the oxidation number has gone down, so it's been reduced. Let's look at the chlorine. Well, it's got a -1 oxidation number there. And it's also got a -1 oxidation there. So those 2 chlorines, nothing's happened to those 2. But look at these chlorines here, that's 0. So something has happened to them. It's gone up. The oxidation number has gone up. So the chlorine has become oxidized there. And that probably wasn't immediately apparent from looking at that equation. So that's where oxidation numbers have helped us there to work out what's going on. And let's just do our oxidizing agent thing. Well, the manganese is being reduced, so this is the oxidizing agent, isn't it? The chloride ions, well, some of them have been reduced, so they are the reducing agents. Okay, so that one was a bit more tricky, and then I think then the last one I've got here is definitely more tricky. So let's get rid of that. And do the last one. I've just got this one left down here. Right, so I am going to break that down into, I'm going to break that down into ions because we've got potassium there. We always know potassium is always +1, isn't it? So we've got this potassium dichromate there. We've got 2K plus ions, and we have got the dichromate ion. And you can tell that the formula of that must be 2 minus charge on it because you've got 2 pluses from the potassium. Potassium hydroxide, we've got 2 more potassiums there, and so we have got 2 OH minus ions. Now here we have got this compound here. We can break that down. That must be, right, you must have CrO4 2 minus because you've got, it's K2, yeah? And how many of them we've got? We've got 2 of them. And that means we've got 4 K pluses. And we've got an H2O. So let's look at oxygen first of all, because that's easy. Well, let's look at potassium. Spectator ions, we know nothing's happening there, yeah? No change in oxidation number of potassium. Let's look at the oxygen. Right, oxygen there in its compounds always -2. It's -2 there, -2 there. It's -2 there, and -2 there. No redox going on with the oxygen. The hydrogen, we have got +1 there, always +1 in its compounds, always +1 there, really easy, nothing happening with the hydrogen. So the only element we've got to look at now is the chromium. Okay, let's look at the chromium. Now, what is the oxidation number of chromium here? Right, so sigma oxidation number, it's a very bad sigma. Sum of the oxidation numbers is equal to the charge, remember? So we have got the charge is -2. Chromium we don't know, there's 2 of them, so 2Cr. Each oxygen is -2, so that's -14. So we work that out. Chromium is equal to +6 oxidation state there. Right, let's have a look at the oxidation number of chromium in this chromate ion. So again, the charge on the species is -2. We've got 1 chromium. We've got 4 oxygens, so that's -8. So chromium is equal to +6. So you can see the +6 remains +6. So the chromium hasn't been oxidized or reduced, and so that reaction is not a redox reaction. And it would be pretty hard to tell that without using oxidation numbers. Okay, so I think we'll do more examples of that later, but we'll leave that there for now.